Okay, so when we look at the questions on our Unit 8 review, when we want to find the number of orbitals that are in a sublevel, remember, if you just look at your periodic table and you look at those different blocks and you take 2 elements at a time, that will tell you how many orbitals to draw. So how many are we going to draw if it's S? 1. If it's P, we're going to draw 3 little dashes. If it's D, we're going to draw 5 orbitals. And if it's F, it's going to be 7. 1, 2, 3, 4, 5, 6, 7. There are odd numbers. 1, 3, 5, and 7. If we want to know how many electrons are in each one of those sublevels, how many electrons fit in one sublevel? Or one orbital, I mean. One orbital holds 2 electrons. So if you just take your number of orbitals, multiply times 2, that will give you the number of electrons in that sublevel. So S is going to have 2 electrons. P is going to have 6. Remember, if we have 3 orbitals, 2 electrons in each, we have a total of 6. D is going to be 10, and F is 14. On your test, that's going to be 8 different questions out of the 30. So for the next little section, we have to come up with 4 different things for our element. The first thing we want to come up with is orbital notation. That's the one with dashes and arrows. So we look up potassium on our periodic table. What group is it in? 4S, right? 4S. So we're going to list all of our sublevels until we get to 4S. So the first one is going to be 1S, then we will eventually do the shorter version. Yes. We're going to do all of the different types of writing for the electrons here. So we have 1S, then 2S and 2P, then and 3P. And that's where potassium is, so that's where we're going to stop. Everything before this last sublevel gets filled with electrons. So we'll have up, down, and all of these except for 4S. And then in order to figure out how many electrons we need in that last sublevel, we look at the little 4S section and we see where is potassium. If it's the first element, we just need 1 arrow. If it's the second element, we need 2 arrows. And it's the first one, so we just need 1 arrow. Okay. So that's the orbital notation. The next thing we need to do is the electron configuration, which is going to be quite similar. It's instead of drawing dashes and arrows, though, we're going to write how many electrons are in each sublevel. So we're going to have 1S, and then what number are we going to write up above the S? A what? A 2. There's 2 electrons there. And then we have 2S, 2, 2P6, 3S2, 3P6. And if we kept going, we'd put 4S2 and keep going, but we want to stop here. We only need 1 electron there, so it's 4S1. So that's the electron configuration. Okay. The abbreviated electron configuration, we have to look and see which noble gas, which element in that very last column, is closest to potassium without going past it. That's going to be argon, number 18. Okay. So we'll put argon symbol in brackets, and that takes us through the end of the 3rd row. So that means then we continue on starting at the beginning of the 4th row. So that's going to start with what? 4S, and we just want that first element, potassium. So that's the abbreviated form. And then the last thing we want to do is come up with our quantum number set. So what we need to do is look at the very last electron we drew for orbital notation. So we're looking at this electron right here. How do we come up with the first quantum number? This number right here. So that's going to be energy level 4. Then we look at what type of sublevel it is. S is going to be 0. Right. We look at the position. Which orbital is it in? The middle position 0. There's only 1 position available. And then it's an up arrow, so it is a positive 1/2. And we'll go over the first thing on the back, again, how we come up with those numbers. Okay. So we're going to do the same thing, only now we're going to look at polonium. Where is polonium on the table? PO. Okay, it's number 84. So we've got to go from the very beginning at 1s all the way down there to 6p. That's the sublevel it ends in, is 6p. So for the orbital notation, we'll do this together. We've got 1s, then 2s and 2p, then 3s and 3p, then 4s, and this is fourth row is when it gets funny. After 4s we have 3d with 5 orbitals, and then 4p. What's next? 5s, then 4d, 5p, 6s. We're not going to go to 5d quite yet. What do we have to go to right after 6s? Yes, we have to go down to the f sublevel. There, the bottom row. It's going to be 4f. How many little orbitals? 7. And then after 4f, we have 5d, and then 6p. Whoop, I did that funny. And that's where polonium is, so that's where I'm going to stop. Everything except for 6p needs to be filled with electrons. So we go up, down, and you're just going to fill these in. Really remember, because of Hund's rule, we would have all the up arrows filling in and then all the down arrows. But since we know these are going to be full, we can just kind of go through and go up, down on each one. And then whenever you get to 6p, that's where we're going to have to look and see, well, where in that sublevel do we actually find polonium? And we count over, and how far over is it? It's the fourth one over. So that means we're going to have 4 electrons to fill in here. Hund's rule tells us we're going to go one at a time until they all have an up. And then if we need any more, which we do need a fourth one, then we can go back and have a down arrow. And that's the last one that we drew, so that will be the one that we focus on whenever we come back and do our quantum number set. So if we're going to write the electron configuration for this, it'll go a little bit quicker because we won't have the dashes and arrows. We'll have 1s2, 2s2 and 2p6, 3s2 and 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, and then for 6p, that's where we look and see, well, how far over was it? It was the fourth element over, so it's just 6p4 at the end. And if we wanted to do the abbreviated form of it, we'd have to find the noble gas that's closest to polonium without going past it. So polonium's number 84. We might be tempted to pick radon because it's just a couple away from it, but that goes past polonium and we can't do it. So it is going to be Xe, xenon. So we'll put Xe in brackets. And xenon's at the end of the 5th row. So that means that we'll continue on starting at the beginning of the 6th row. And so that's going to be starting right here. And we'll just copy from that point on. So we would have 6s2, 4f14, 5d10, and 6p4. That's the short version. That's the abbreviated electron configuration. And for the very last thing we want to do here, we want to find the quantum number set. So we look at that very last electron that we drew up here. What's the first quantum number going to be? A 6, we get that from right there. And then a 1, P is going to be a 1. And then negative 1 because we're looking at the position. The middle position is always 0. We go back a spot, that would be negative 1. If we went forward a spot, it would be positive 1. And it's facing down, so it's negative 1/2. It's a down spin arrow. Okay. On your test, it's going to be multiple choice, so you won't have to actually draw the orbitals with the electrons in it, little dashes and arrows. You just have to choose the one that's done correctly. Okay. Okay. On the back, we have a place to talk a little bit more about quantum numbers. You don't have to know the names for them or the letters that we use to represent the 4 different numbers. You just need to know what they're telling us. So the very first quantum number is telling us which energy level we have. So for example, if it's 4s, our first quantum number would be a 4. It comes from right there. If it was 6p, then it would be a 6. It would be that number right there. Yeah. Actually, it's an n, a lowercase n. If you wanted to know the letter. Those are the little symbols if you wanted to have them, but you don't have to know them on your test. Okay, our second quantum number has to do with which sublevel we have, which sublevel or subshell. And each different letter has a different number that goes with it. So if it's S, it's going to be 0. If it's P, it's going to be 1. If it's D, it's 2. And F is 3. SPDF, yeah. That goes in order. Our third quantum number tells us which orbital that electron is found in. And just remember the middle is always going to be 0. So if I have an S sublevel here, then that middle value is going to be 0. If I have P, whoops, the middle position is still 0, and it's like on a number line. If I go to the left a spot, that number is going to be a negative 1. If I go to the right a spot, it's going to be a positive 1. If I have D, the middle is still 0. We still have the negative 1 and plus 1, and then we just go out one more number. So one more past negative 1 would be negative 2. One more past positive 1 would be positive 2. And then if we had F, again, the middle is 0. And then we just go from there. Negative 1, negative 2, negative 3, plus 1, plus 2, plus 3. What does the last quantum number have to do with? The spin of the electron. And it does matter if it's up or down. If we have an up, it's going to be plus 1/2. If it's down, it's going to be negative 1/2. So that's how you come up with those 4 quantum numbers. And I'll have that little thing that you use to help you on your worksheet where the little box that was up at the top, they kind of gave you little hints about it. So are we going to have to write that, or is it going to be like matching? It'll be like a matching. Okay. On the next thing, this has to do with what we were talking about on Monday, where we're looking at the different characteristics of a wave of light. And if we have the frequency of a wave, remember frequency is telling you how many waves are going past every second, like from what top of the wave to the top of the next wave, a wavelength. So if we double the frequency, if we make twice as many waves go by every second, what is that going to do to the energy? Is it going to increase it or decrease it? It doubles also, it increases. The more waves you have going by every second, the more energy it has. Those two are directly proportional, frequency and energy. So if I'm getting twice as many waves going by every second, what happened to my wavelength? It got shorter, it got cut in half. And that's the type of relationship you're going to have to be able to recognize on your test. It'll be questions very similar to this. There will be some extra credit questions where I'm going to give you the 3 formulas we learned yesterday, like the C equals F lambda and E equals HF, and the constants that you would need to work with those. And if you can plug in your numbers and solve it, then you can earn some extra points. So just like how we found the wavelength of the radio station on the worksheet yesterday, you will be able to earn some extra points for being able to work with those. But I'll give you all the formulas and all the constants. Okay, if the wavelength of a wave is tripled, we've got a wave that's a certain length and we triple that, what's going to happen to the energy of that wave? It's going to decrease. It's going to get smaller. It's going to be cut by a third. Because they're inversely related, right? It's an indirect relationship. So what's going to happen to the frequency if my wave is 3 times as long? Okay, think about what frequency means real quick. Frequency is talking about how many waves are going past every second. So if I made my wave longer, I'm going to have fewer waves going by every second. So the frequency also gets cut by a third. Remember, energy and frequency are the ones that are directly related. So if energy was cut by a third, frequency was also cut by a third.
Those are the only ones that are same, but the other ones are opposite.
Mm-hmm. Okay. Now, on your test, I'm going to give you this little section right here. And it's already going to be filled in with what we're going to fill in here. So we're going to go ahead. We've got time. We're going to fill in visible light in the middle. On your reference sheet, you're going to have this that you can look at. So you need to know Roy G. Biv, though. You need to know the order of the colors here. And so then we've got ultraviolet, X-ray, and gamma rays. Gamma is the shortest. And then on this side, radio is the longest. Then we have microwave and infrared. What you will need to know, again, is the colors in the visible spectrum here, as well as which side has the long wavelength, which side has low energy and low frequency. So on the left-hand side here, we're going to have long wavelength, we're going to have low frequency, and we're going to have low energy. On the right-hand side, we're going to have short wavelength, high frequency, and high energy. So just remember, on the left-hand side, you have all the L's. Long, low, low on the left. The very last thing here, we want to identify which element we have from the electron configuration. You only have to look at the very last one. So you just go and pinpoint where that little square is on your table. It's kind of like a coordinate. You go to 3D, the top row of the transition metals. You count 5 elements over, and we get manganese, Mn. For 3p3, you go to the third row, go over to the p block, count 3 elements over, and we get phosphorus. For 5s1, you go to the 5th row, the s block's there at the beginning. The very first element is rubidium. And you don't have to do the abbreviated electron configurations for those. So your test will be multiple choice and matching. The only short answer one will be explaining how fluorescent substances glow.